Hi and Assalamualaikum warahmatullahi wabarakatuh. My name is Zanur Hisham bin Muhammad Izzaruddin. My matrix number is CD240291. Today our group will present about a case study of a bicycle wheel and pedal motion, prepared by Group 12. So next, our group members have 5%, which is one Arits bin one Sarman. The number matrix is CD240212. Next, we have Nurul Ain Atira binti Abu Hassan. The number matrix is CD240231. The third one, we have me, Zanur Hisham bin Muhammad Izzaruddin, CD240291. Next, we have Yo Yongjia, the number matrix is DD240144, and the last one is Sharwin, anak lelaki Siva Kurma, the number matrix is CD240031.
For introduction, dynamic is a fundamental subject in mechanical engineering that study the motion of bodies and forces that cause motion. It consists of kinematics, which describe the motion without considering force, and kinetics, which relate motion to force and moments. Kinetic of rigid body assume no deformation, allowing simplified yet accurate motion analysis. In this project, rigid body's kinetic is applied to a bicycle wheel and a pedal system, where the wheel experiences both translation and rotational motion. Different points on the wheel and pedal have different velocities, making the system suitable for real-life dynamic analysis. For the objective, this project is used to understand the fundamental principle of kinetic of rigid bodies. Secondly, to study the relationship between translational and rotational velocity of a bicycle wheel. To apply the relative velocity concept in analyzing the motion of the bicycle pedal. To determine the maximum and minimum absolute velocity of the pedal during the motion. And lastly, strengthen the application of dynamic theory using a practical cycling example.
Assalamualaikum warahmatullahi wabarakatuh. My name is Zanur Hisham bin Muhammad Izzaruddin. My matrix number is CD240291. So I will continue case study description. Our case study examines the dynamic effect of a cyclist riding on a flat road at a constant speed of 15 km per hour. This scenario is particularly relevant because it accounts for a slight headwind, which acts as a recessive force similar to cyclists uphill. This mirror real-world condition encountered in a long-distance cyclist or road race. In this model, we treat the bicycle wheel as a rigid body, meaning we neglect any deformation of the key assumption in our analysis is the wheel undergoes pure rolling motion without slipping on the road surface. To determine the absolute velocity of the pedal, we must understand the two simultaneous motion occurring, the translational motion of the bicycle center and the rotational motion of the wheel and pedal system. The pedal system is attached at a fixed distance from the center of rotation. Our primary goal is to identify the maximum and minimum magnitude of the pedal's absolute velocity during one full rotation. This extremely occurs when the pedal's motion is either perfectly aligned with the direct opposite to the bicycle forward direction.
Greetings, my name is Wan Alvaris bin Wan Sarman with the matrix number of CD240212. So, in this study, our methodology is based on the principle of the relative velocity, a fundamental concept in the kinetics of rigid bodies, used to analyze the maximum and minimum absolute velocities of a bicycle. Velocity is treated as a vector quantity, meaning both magnitude and direction must be considered relative to a chosen reference frame. Relative velocity is determined by taking the algebraic sum of speeds when bodies move in opposite directions and the difference in speeds when they move in the same direction. When analyzing road race performance, relative velocity helps explain why a headwind feels like an invisible wall, While the cyclist's ground speed may remain constant, the air moves in the opposite direction, increasing the resistance and affecting the forces experienced during pedaling. This motion is described using the equation VA equals to VB plus V in bracket A divided by B, where VA is the absolute velocity of the pedal, VB is the forward velocity of the bicycle, and V in bracket A over B is the pedal's velocity relative to the bicycle frame. The forward velocity of the bicycle is related to wheel's rotation using V equals to R omega, where R is the radius of the bicycle wheel and omega is the angular velocity of the wheel. This shows how rotational motion contributes directly to this bicycle's linear speed. Because the pedal rotates with angular velocity omega, its linear speed is not constant throughout a full revolution. The pedal reaches its maximum absolute velocity at the top of the stroke, where its rotational motion adds to the bicycle's forward velocity. Under a headwind, this is when the rider encounters the highest air resistance, making the stroke feel heavy. At the bottom of the stroke, the pedal's motion opposes the bicycle's direction, resulting in a minimum absolute velocity and reduced resistance. This continuous variation in the velocity explains why a headwind not only slows the cyclist down, but also makes pedaling uneven and physically demanding. Thank you.
Hi, Assalamualaikum. My name is Nura Ain Atira binti Abu Hassan and my metric number is CD240231. Next, I will explain the calculations used in this project. In this study, the principle of relative velocity and rigid body dynamics was applied to analyze the motion of a bicycle wheel and pedal system. The cyclist is assumed to ride a constant speed of 50 km per hour, which is equal to 4.167 meter per second. The wheel radius is 0.35 meter and the pedal is located 0.16 meter from the center of rotation. Under the assumption of pure rolling without slipping, the angular velocity of the wheel can be calculated using the equation omega equal to V per R. Substituting the values, the wheel angular velocity is 11.91 radian per second. Next, the angular velocity of the pedal is determined by considering the sprocket and chainring ratio. Using this ratio, the pedal angular velocity is calculated as 5.104 radian per second. The relative velocity of the pedal with respect to the wheel center is then obtained using the equation V equal to omega times R. This gives a relative velocity of 0.817 meter per second. Finally, the maximum and minimum magnitudes of the absolute velocity of the pedal are calculated using the relative velocity equation. The maximum velocity occurs when the pedal moves in the same direction as the bicycle motion, resulting in a value of 4.984 meter per second. The minimum velocity occurs when the pedal moves in the opposite direction, giving a value of 3.350 meter per second. This result demonstrates how the combination of translational and rotational motion affects the velocity of the bicycle pedal. That's all for me. Thank you.
Study analyzes the motion of the bicycle wheel and the pedal using the principle of rigid body dynamics, which involve a combination of translational and rotational motion. A constant speed of 15 km per hour, the bicycle undergoes a condition of pure rolling without slipping, allowing relationship to be applied because the point of contact between the wheel and the ground has zero relative velocity. The relative velocity method is used to determine the absolute velocity of the pedal by combining the translational velocity of the bicycle with the rotational velocity of pedal relative to the wheel center. The result shows that pedal velocity is a maximum when the pedal rotation is in the same direction as the bicycle motion, and minimum when the pedal rotational opposite to the direction of the bicycle motion. In conclusion, the bicycle wheel and the pedal system serves as an effective model for understanding the concept of translational motion, rotational motion and relative velocity in rigid body dynamics. This is successfully links kinematic theory with the real engineering application in real-world situation. However, the analysis can be improved by considering additional factors such as friction, air resistance, and road gradient. In future, studies may also incorporate the effect of acceleration and deceleration as well as the use of simulation or experimental data to extend the accuracy of the results.